Here's another example of solving a system of linear equations using an augmented matrix and performing Gauss-Jordan elimination. All right, so here is the example, and I want you to notice that in equations 1 and 2, we are missing the variable z, which means that in the augmented matrix, I'm going to have zeros. Similarly, in equation 3, we're missing the variable x, so there's going to be a 0 there. Now, for time purposes, the way that I've written this out, you're not going to see the augmentation bar where the equal signs get replaced by an augmentation bar in that augmented matrix. So I want you to imagine it's still there. One more thing here before I start to show that. Since our first step is going to be getting a 1 in the upper right-hand entry, I don't want to do that with multiplying everything in the first equation by 3, because that's going to give me a fraction on this one that is less nice. Whereas if I interchange equation 1 and equation 2, so that I would interchange row 1 and row 2 in the augmented matrix, if I divide everything by 2, I'm still going to wind up with a fraction, but with a nicer denominator. All right, here we go. I've entered in the augmented matrix. Again, remember that we're viewing this as having an augmentation bar between column 3 and column 4. And I'm showing the interchange of the first and the second row. And then what I'm going to do is make that 2 a 1 by multiplying everything in row 1 by 1/2. I need to use that 1 that is in row 1, column 1. It's along the diagonal. I need to use that to make that 3 into a 0. I don't have to do anything with row 1 changing row 3 because I already have 0 in that column. So I'll multiply by -3 to everything in row 1 and add it to row 2. So we had -3 plus 3, +9 plus 12, 0 plus 0, and -3/2 plus 5 to give us this 7/2 here. I've shown in a previous video where you can do these row operations using a TI-84. There are additional shortcuts that I don't think are wise to get into showing, not at this stage of the game. I'm going to link the video where I've shown doing individual row operations. Just checking something in my head here. Okay, yep, that works. All right, so now I've got a unit column in that first column. So I move along the diagonal to the 21, and I want to make that a 1. I'm going to multiply everything in row 2 by 1/21. Okay, so just focusing in on that one particular portion of the row operation currently being examined. Well, 21 is 3 times 7, and that's good because then we've got a 7 in the numerator over here and a 7 in the denominator here. Since we multiply straight across, we can reduce straight up and down or up and down diagonally. So 1/3 times 1/2 gives me the 1/6 that we saw just a moment ago. So let's go back to that. Right, we had that 1/6. So now we need to use the 1 that's in row 2, column 2, to change the rest of column 2. I will be multiplying everything in row 2 by 3 and adding it to row 1 to make a new row 1. And similarly, everything in row 2 by -6 and adding it to everything in row 3 to get a new row 3. So that we'll have a unit column in column 2 without doing anything to mess up what we had in column 1. And finally, now that I have column 1 and column 2 as unit columns, to get column 3 to be a unit column, all I need to do is multiply everything in row 3 by a 1/2, and we've already got zeros above that entry along the diagonal. And so then reading off the solution coming up next. All right, so I have copied over here the final matrix that we had, including the augmentation bar and what we see here. And remember that that first row, you could read that as saying 1x plus 0y plus 0z equals 1. And a whole bunch of that would simplify to just say that x equals 1. Similarly, y equals 1/6 and z equals -5. Whether you have to write that as an ordered triple, or you can state separately, x equals 1, y equals 1/6, and z equals -5. That's going to depend. Hope that helps.